So, welcome back. I hope you enjoyed networking. It seemed so by watching you. So, here is our next speaker, Philipp Niedermeyer. He's head of research and development of Alpitronic. He finished his Master of Technical Physics, like me, at the Technical University of Munich, and joined Alpitronic in 2014. Since 2018, he's a team leader of system development, and as I told you before, now it is getting hot because the electronic companies, they produce the heat, which before we heard can sometimes are some problem and has to be transported away in the controlled conditions. Please, for your talk.
Thank you, Johannes. Actually, I'm not head of research and development. I'm head of system development. The head of research and development, so our CTO, is Andreas Oberach. He wanted to give this speech in the first place. He sends the regards, and unfortunately, he could not make it. But I'm here instead of him. I'm starting the presentation with a brief introduction and overview of what Alpitronic is, what we do. Actually, Alpitronic was founded in 2009, and for the first 5 years we were located in the TIS, which was the predecessor of the Neu Tech Park. And these are the four founders, Andreas Oberach, our CTO, and Philipp Senono on the right is our CEO currently. And the history of Alpitronic is that for the first 8 years we mainly developed power electronics for EV cars, so battery electric vehicles and also hydrogen vehicles. And we did this mainly on a prototype level. And another quite important business part was the production and development of those test benches, which are the power cycling test benches with which we are able to test the lifetime of power electronic modules. We will see that later. Since 2017, Alpitronic is mainly focusing on the development, production, and let's say selling of the hypercharger, which is our main product. In the meantime, it became a product family. We have three different power levels: 50 kilowatt, 300 kilowatt, and 400 kilowatt. We will see that later. And we are selling that currently in all over Europe. We are now in the completion of the certification of our chargers for the US market as well. This is why we founded the headquarters for the Alpitronic US in a few months ago. In Europe, of course, our headquarters in Bozen with the production repair center and the central warehouse. All the R&D is also in Bozen with two let's say, satellite offices, one in Munich and one in Bologna. In Bergamo, we have a remote support center as well. Some numbers. We are currently over 800 employees. We're trying to be a 4-digit number of employees within the end of this year. So as you can see, since we started this hypercharger product in 2017, more or less every year we managed to double the number of employees. Mainly, of course, due to the high percentage of employees in the production. And here is a very high-level overview of our product. So this is the hypercharger, which is currently you can get on the market in two, let's say, power ranges. One is the 300 kilowatt, which is, let's say, the old IGBT technology, and one, the 400 kilowatt, which uses silicon carbide, which is on the market since a few months. The main task of the charger is to convert the AC current of the grid to DC current, which is charging the battery of the electrical vehicle. This is done in let's say, in a certain amount of steps. First of all, there's the input switchgear, which is providing, which is connected to the grid and which is then distributing the AC to the single power stacks. The power stacks is, let's say, our component which is doing the AC to DC conversion, and it's a modular concept, meaning that you can take up to currently 4, in the future we're trying to increase that number to 8 of those power stacks in parallel, and so you can scale the power of the charger. The output switchgear is then paralleling the DC output of the single stacks towards the car, which is then of course charged via the charging cable. Today, of course, if we're talking about thermal management, we are talking about this red path, which is, let's say, the power path, the path where all the power flows. Just to give you a rough number, if we talk about the 400 kilowatt charger, we have currently an efficiency of somewhere around 96 to 97%, which means that in the worst case, we have to get out 16 kilowatt of this charger. And what is maybe a little bit different to what we have seen in the earlier presentations, where we mainly talk about liquid cooling in the EV car, our chargers are air cooled. So we use forced air cooling, with one exception, which is the charging cable, which is some charging cables. There are different charging cables the customer can configure. Some of them can be liquid cooled. And today we're not focusing on all this yellow communication path, which is somehow the low-level electronics around all this. This is a map which is showing all the locations of the single hyperchargers, which are currently mainly in Europe. Now we are starting to sell in the US as well, so I'm looking forward to have this map maybe in a year of America as well. Some numbers, we have currently almost 16,000 chargers in the field. The interesting thing, and this is also quite important for thermal management, is that we have a SIM connection to all of our chargers. So they have a SIM card inside, and we can read out a lot of very important parameters. In terms of thermal management, we can read out a lot of different temperatures of different components inside the charger. I think as this slide is a few weeks old, I think we reached the magical number of 1 terawatt hour of charged energy since we started this adventure with the hyperchargers. So getting to the point, thermal management, I have 3 slides on why this is important for the EV charging infrastructure, and I have 4 main reasons why the market requests solution for let's say, an efficient thermal management. First of all, volume, power density, and weight. The market requests compact charging solutions. Space is limited everywhere, so one of our big unique selling points is that we have very compact chargers. So they are more or less, it's half of, let's say, the volume, the power density of other chargers of other competitors. And if you have a look at the physics, so the 3, let's say, physical laws which define on how you get the heat out of your power electronics, they all have one thing in common, which is the surface. So if you want to get smaller, you need to take this into account, and if you have a certain power loss and you want to get rid of it, you might think that you need to increase the surface to get bigger. But if you do the math and if you calculate the power loss density. So if you want to get rid of a certain power loss density and optimize it, you actually need to get smaller. And this is, let's say, this is the task, and this is the difficult thing in the thermal management. This is, I think, quite impressive graphics as well. So the temperature we're dealing with is somewhere in the range of above 100, 150, in some cases 175 degrees. And the power loss density we're dealing with is somewhere around 1 watt per square millimeter. So I brought some power modules. This is actually the one which is in the picture over there. So 2/3 of all the power losses we're making in the power electronics is made in the power electronic, let's say in the power transistors, and they have around about a power loss density of 1 watt per square millimeter, which is in the same league as for example, rockets, and which is order of magnitude higher than, for example, a cooking plate. Second, very important topic why thermal management is important is the efficiency. The market demands high efficiency. So basically, our customers, which are the operators of the chargers, they buy the AC current from the energy provider, and they sell DC current to the drivers. The power loss, which is, or the power which is lost in the middle, in the conversion, it's basically their operation cost. So the better your efficiency is, the better it is for our customers, the more money they can save. Now, if you have a look at most of the, let's say, loss physics, you can see that losses increase with increased temperature, which is, of course, the reason for the thermal runaway of most components. So this is, for example, the resistance of those silicon carbide transistors, which is increasing with an increasing temperature. So you need really to have a good thermal management in order to keep the transistors cool, also in order to keep the efficiency high. And of course, what we try to follow is what's written here. The best thermal management starts with the first step, which is avoid power losses. A third very important reason for why we need a good thermal management is noise. The chargers are very often installed in urban areas, so the noise is an important topic. So they're close to houses, and they're very often you need to do a study of how loud the charger can get in certain operating points. And of course, if you optimize your thermal management, you can maybe get rid of some fans. You can reduce the number of fans, or can you reduce the speed of the fans, and optimize your noise emissions. Here you can see a charger which is the noise measurement of the charger inside an anechoic chamber. The last but not least, let's say, motivation for why thermal management is important is the lifetime and the reliability. Our customers, they require reliable chargers. It's part of the critical infrastructure, so we really need to be sure the chargers work day and night, and they do this job for at least 10 years. And if you have a look at most power electronic components, and if you dive into the lifetime calculations of the power electronic components, you see that the lifetime limiting factor is the thermal swing they do, let's say, at every charging cycle. So this is one typical day of a charger, and you can see some temperatures of some of those power modules. And for every charging session, you see that the module gets heat up and then cooled down after the charging session is over. And these thermal swings, they add up and somehow limit the lifetime by defect mechanisms, such as, for example, the bond wire liftoff inside the module. Here, I think I've seen this in a slide earlier. A rule of thumb is if you are able to reduce this temperature swing by 7 Kelvin, I think in the slide earlier I've seen 10 Kelvin, you can double the lifetime of such components. Okay, so I try to give you a very high-level overview of how we tackle let's say, the thermal management, the thermal design of our power electronic converters. And our first step is, of course, we need to identify heat sources. So what are the heat sources? I mentioned earlier, 2/3 of the power losses, they are made in the power electronic component. Now, usually, what you do is to calculate on with the mix of analytical and numerical simulations the heat or the power losses of the semiconductors for all the combinations of different operating points. So in this case, output power and output voltage. And you have to do this very carefully and let's say include really all the operating points, because I put on the slide this example because here you can see that for this module, for example, the worst case operating point is not at full power but close to zero power, which means that you really need to take into account all the different operating points. And the difficult task in the power electronics is, of course, the power losses which are made by parasitic components, which maybe at the moment you are designing your system are not well known. So this is something you usually identify very late in the let's say in the development phase, and this usually causes a lot of trouble too late in the development phase. And this is why we usually try to, at very early prototype stages, try to see if our calculations, our simulations of the heat sources, also of the power losses inside the main components, if we calculated them right. And this, of course, we need to do with measurements. So we compare our simulation results with measurement results. For example, in this case, I showed you the temperature, maximum temperature of the transistor in the different operating points. The lines are the simulated results and the dots are the measured results. And in this case, we were able to, let's say, get simulation and the reality within a very, very reasonable distance. And after you identified the heat sources, of course, the main task is to dimension the heat sink and cooling paths. In this case, we usually use simulation tools, in this case ANSYS, to simulate temperatures in real operating conditions. What I show here is the temperature of a heat sink, and in the first simulation step we saw that the maximum temperature, again, of a module like this exceeded the maximum allowed temperature of, in this case, 80 degrees. And what we did is we introduced heat pipes, and the optimization of this design we did in a simulation where we were able to show that by introducing heat pipes we decreased the maximum temperature of the components by more than 10 degrees, which was then, let's say, satisfied our requirements, and with this design we then went into the production. The last step after identifying the heat sources, simulating the thermal behavior, is the test. A large part of the tests in our power electronic lab is temperature tests, thermal tests. This usually takes several months to really measure measure all the different temperatures of the single components in all different operating points. And in the picture here in the middle, you can see a charger which is equipped with around about 80 different thermocouples at different spots inside the power electronics. So all the critical components, they must be monitored with the thermal couple, put inside climate chamber and measured in all different combinations of different operating points and ambient temperatures. Usually we do this with thermocouples or with infrared cameras, and this test they then are the input for the redesign phases, where you then try to optimize the thermal behavior of components which, let's say, exceed or are close to their thermal limit. In the end, I wanted to show some pictures of thermal tests we did also here at the Neue Tech Park. So one quite, let's say, big problem is irradiation of the sun. So we do not only have to deal with the power losses we create inside the power electronics, but also with irradiation of the sun, which on our chargers. We tested this in the lab, which is here at the Neue Tech Park, where we were able to simulate the radiation of the sun on a charger, and we're able to test this in different ambient conditions. If we're talking about thermal management, we also need to consider not only the worst case, which is in our case usually 55 degrees ambient temperature, but also negative temperatures. So good thermal behavior also takes into account the negative temperatures. So cold starts are quite an important, let's say, an important test for us. This test we did in the big climatic chamber of the Neue Tech Park, and what usually happens at cold starts is you have to make sure that all the electronics, the wake up of all the electronics after a cold night, after snow, after heavy rain is still working, and this is also quite extensive tests we need to do at the end of our design phase. I think this was the last slide.
Thank you very much, Philipp Niedermeyer. So we are exactly in time, so I would invite you to ask maybe in the aperitivo session afterwards if you have some questions. Thank you. I would like to present you the next speaker. It is Dr. Nicola Zorzi, Senior Mechanical Engineer at Danfoss. Nicola Zorzi did his master in aerospace engineering in Padua. He worked at Hyper-3 Solution SRL and Iveco DVD before he changed to Danfoss in Burgstall, in Postal, where he did 9 years of combined experience in the drives and automotive sector, CFD and FEM simulations, and he will talk about power electronic products, how to keep cool.
Okay, thank you for a nice introduction. My presentation is slightly different between the others because I'm going deep down in details, and I'm going to speak about the design optimization of PCB through numerical simulation. But before starting, let me spend a couple of words on Danfoss. Danfoss is a multinational company based in Denmark with more than 42,000 employees globally. Danfoss has 3 segments. The first one is power solution. It mainly design and produce hydraulic pumps, hydraulic motors, hydraulic steering system. The second segment is climate solution, focused on heating and cooling buildings. So design and produces valves, compressor, heat exchangers, components for heat pumps. And the third segment is power electronic and drives. One out of 17 factories is placed in Merano. And there we are responsible for all the process from the idea, the concept, to the serial production of drives. We are specialized in drives especially for the food and beverage industry, so different between automotive industry. And our, let's say, amount of production is more than 70,000 drives per year. Okay, so let's go on and let me introduce the topic and a brief introduction of the topic and the methodology we used. I'm going to speak about a problem we dealt with. So, brief introduction. This is servo drive. This part is the motor, and this is the all electronic part, in which the power board is placed. The power board, let's say, it could be considered like the heart of the drive. And in the power board, we find these two connectors here that are important for this study, because the first functional test on these drives failed due to excessive heat temperature on M23 connectors. So to solve this problem, a new enhanced alloy was adapted for the pins. And so functional tests were completed, but the device temperature was still too high, and we see beforehand that 10 degrees of more of the components are reduce the life. This picture here is taken from a thermocamera, and we can see how the pins of the M23 connectors plays a big role on the heat dissipation. And, but unfortunately, we have no more possibility to improve the pin alloy. So what we done, we used the thermal simulation to understand the problem, to understand where are the problems, and guide the design process to a temperature decrease. In this case, electrical simulation have been coupled with thermal simulation. We used the ANSYS suite for both electrical analysis and thermal simulation. We coupled these two software till convergence is reached, because for the CFD simulation we need the temperature from the electrical analysis, and the electrical analysis depends on the temperature that is an output of the CFD analysis. This is the computational model, so we can see the various layers of the PCB. Here we can see the nets, and regarding the boundary condition, appropriate continuous current was imposed on the printed circuit board. Regarding the computational model of the thermal side, it's possible to see the case. So the aluminum case, this green is the power board, and this is the module. That is possible to see here in detail the module with the 6 chips that dissipate powers. And this is the power board. And since the pins are important for heat dissipation, here pins are modeled as cylinders with thermal loss. We are in natural convection, so laminar flow was chosen, and we also consider the radiation model. So let's now move to the current design. This step is important to validate the simulation and then proceed with the design optimization improvements. So we can see here some nice pictures from the CFD analysis. Streamlines can be seen here. We colored by temperature, while on the right side, cross-section of the internal side of the drives can be seen. We can see here, we can see the power board that's hot here, almost more than 100 Celsius degrees. And this is the output from the electrical simulation. So we can see where are the, let's say, the problem. And with simulation, it's possible to understand how big are the loss inside the power board. We can see here that the loss inside the power board are comparable with the loss of the pins. Regarding the CFD analysis, the temperature of the power board is found, and we can see how the high temperature is placed between the M23 connector. And okay, this simulation, as I said before, was the main purpose was to validate the simulation. And these are in this table are shown the simulation output compared with the test. So we have good correlation between the two tests, so we can consider the simulation correct, and we can proceed with further improvements. Last slide with the case temperature, so we can see a hot spot here because it's in contact with the module. So, and outside we reach up to 95 degrees. So now we can proceed with with improving geometry, and several geometries have been studied. In this case, to enhance the thermal dissipation, a thermal pad was placed between the M23 connectors. So basically, these are some of the geometry we studied. The first little thermal pad, a small thermal pad was put, and then for the version 3, a bigger thermal pad. We would like to understand the contribute of the thermal pad. These are some pictures that show the coverage of the thermal pad on the PCB. Basically, the VU03 is much bigger than the other, but mainly covers the green area that is not dissipate power. So let's move to the result. We can see here how the thermal pad reduced the temperature of about 10-15 degrees, and the size of the thermal pad is not so, let's say, a big difference between the three thermal pads. Only in 0.4, there's here in the graphs is the main difference because the 0.4 is placed just below the thermal pad. Okay, here we can see the temperature of the PCB. So it's possible to appreciate how to see how the temperature is reduced between the connectors because of the thermal pad. So before the thermal pad we have something like 110 degrees, and now the temperature is reduced to 95 degrees more or less. Thermal analysis has the advantages to find some quantities that are impossible to find during the test. For example, it's possible to understand the amount of energy, the heat flow that pass through the thermal pad and the heat flow through the screws. And this was important for the next step because how sometimes happening in this industry after some weeks was necessary to review the entire layout because of mechanical constraint and because of new functionality for functionality reason. So in this case, simulation were used to guide the design of copper trays. The aim was to conduct more heat through the screws and to design wider copper trays to transport the heat towards cold zones. Here we can see the result of this analysis. So on the right side, we can see how copper trays are in this part are much wider than in the original case. This only for thermal reason, not for electrical reason. The new power board has, for that new functionality, has 200 milliwatt more power than the original, but how we can see in the next slide, the temperature between the two power board is the same because of the methodology we used. Now let me finish my presentation explaining you the final test verification that checked if the simulation were properly done. So preliminary test having carried out to verify the simulation. Preliminary because this power board doesn't have the module that is placed here. And also the ambient temperature was 30 degrees and not 45 degrees. This is due to the main purpose of this downgrade is to speed up the time of the test. So some probes were put on the power board, and this is the device. So you can see here the motor is not here, does not exist, and this device was put in the thermal chamber. The results were okay because the temperature reduction is about 13%. So we can conclude that virtual simulation permits to predict the thermal behavior of the device, and in this case, electrical simulation coupled with thermal simulation permits to estimate the temperature of the new geometry and limiting the number of experimental tests and developing time. For example, for this work, 3 weeks for simulation were needed, while 1 week for the final testing. So we can see how the simulation reduced a lot the development time. This is then my presentation. Thank you for your attention.
Thank you, Nicola Zorzi. We have time for one question. Markus?
Your simulation, your ANSYS simulations are always steady-state simulations, or you consider also true time-dependent problems?
In this case, are steady-state simulation, but we also do transient simulation.
Thank you, Nicola Zorzi, for your talk. And then we come to our last but not least speaker. So if anyone of you still have some heat exchange problems, don't be worried. There are people which are specialized to solving these problems as a service. And Fabio Zanotti from the company Veloxia is a senior simulation expert in Veloxia and Technohit. His competences are the integration of design and simulation. He's coordinating computer-aided engineering teams, and he has a deep experience in thermofluidodynamics. He has more than 20 years of experience in industry and did projects for ABB, Bosch, Oerlikon, Saipem, CGC Corporation, and I could go on with many other famous company names. He will talk about analysis and optimization through numerical simulation. Your floor is yours.
Thank you so much, Johannes, for your introduction. So let's talk about thermal management, but thermal management driven by simulation. Okay, how to solve the problem of thermal management and heat exchange, and optimize or improve, anyway, thermal management problems. Let's go on. Okay, I will talk basically of two works that I carry out in the recent past. The first, the fluid dynamic thermal optimization of an oven for line engraving printing, and ventilation optimization of information panels, illuminated information panels. The panels that you see along the highways, in the train station, in the airports, and so on. And at the end, I will talk very quickly about improvement of a cooling fan, of thermal underhood management. Let's start with the first work. I'm talking about the oven that are used to dry out the paper with the fresh ink. The machines that print, for example, money, documents, passport, and so on, they have fresh ink over the paper. The paper enters the oven, is dried up, and then is wrapped up at the end. What we did, this is the final model of the oven. The customer main needs, the pain of the customer, what was? Develop a new solution to improve the performance of the oven, because they want to improve the profit, the performance of the machine. First of all, increasing the airflow rate, because they wanted to increase the speed of the paper into the oven. So they wanted to increase the flow rate of the air, of the hot air that have to dry up the paper, and reduce the startup and the heating times, just to anticipate the start of the paper printing. At the beginning, they took about 40-45 minutes for the warm-up of the machine, of the oven. So every morning, when they switch on the machine, they have to wait almost 1 hour before start printing, because the machine, the oven took too much time to warm up. Okay, so this was another pain that the customer wanted to solve. Other problems: high pressure drop of the air moving into the oven. It means that to move the air, they needed high and strong fans with a very high power absorption and very noisy. And moreover, a non-uniform distribution of the air flowing through the several nozzles that are impinging the paper moving in the oven. So a better distribution of the air through all the nozzles of the blowers, and as I told you before, a long time for warm-up, and then a daily delay in the start of the printing process. So with reverse engineering, we create a 3D model of the original oven, and we create a SFD model of the machine that we analyzed. What we found out, in fact, first of all, a bad, and I go back for a while, a bad design of the, sorry, it doesn't work. Anyway, a bad design of the fan that moved the air. So that was a reason of the high absorbed power and of the high noise produced. And a path, unnecessarily lengthened of the airflow. We noticed that the air did a path useless, and with the high pressure losses, and also high vortices and turbulence that was a cause of the pressure losses. And we noticed also that not all the air went through the battery that had to dry up the airflow, to heat up the airflow. So the original design was bad. So what we did is we started with a new design. So we forced all the air to go through the battery. So all the air at every loop was heated by the batteries. We were able to reduce the pressure losses of the air through the oven, and so we could move a higher airflow rate with a smaller fan, so with a less absorption of power, and with a smaller and less noisy, so a quieter fans, and so also with a better distribution of the air through all the nozzles of the oven, and also we improve significantly the warm-up times, highly reduced, from 45 minutes to less than 10 minutes. So every morning with the new machine, they could start printing early. So what we had is anticipated start time for printing from 45 to 10 minutes is more than the 75% warm-up times gain. Ability to accelerate the paper scrolling through the oven. So with the increase of the flow rate, of course, we could increase the velocity of the paper through the oven, and so we could improve the productivity of the machine. And as I told you before, we have a significant reduction in electricity consumption cost for the fans, because we used a smaller fans, and for the heating batteries. And of course, with a smaller fans, it means also quieter fans, so less noise. So not the workers, as they did before when the machine started, they have to cover their ears due to the very high noise, and this was not needed anymore. So we started from, as I told you before, this is a small recap, the old machine, the 3D model, the CFD model, and the CFD simulation of the old design, bad performances, so we moved to a new design, so a new model. The CFD simulations confirmed the improved performances, and then we realized a new 3D model, a new design, and then this is the new oven that is now working fine and properly. Of course, these sentences and these words are good words for company owners, top managers of companies that are not so technical, they are not engineers like me, but they love those words. Increase in revenues, cost reduction, and so significant increase in profits. So this is an important result of improvement and optimization of thermal management, but in terms of money. The second work, the ventilation and optimization of illuminated information panels. I'm talking about those panels. Okay, in this case, what we found out, the client designed a new model of display, good resolution, very good performance, very light, and so on. But when they tested in the laboratory, what they found out is that the center was clear, but the sides were dark. Why dark? Because the sides were hot. And when the monitor, the display is not ventilated very well, where it is hot, it becomes dark. And this is a problem. And they were about to sell the new display, the new monitors in the Middle East, because they already signed the contract. They had to stop to deliver these panels, the displays in those countries, because they had at the beginning to solve this problem. And they asked me, and they said, Fabio, why we put the fence, the cooling fence there, but why the sides are so dark and they are so hot, and only the middle is light? And so we start analyzing with the CFD simulation the panels, and what we found out is that the front were very well ventilated, as you can see. But the back was bad ventilated. Okay, in the middle, the center was very well ventilated, but the sides, we had these two large vortices with stagnation air that is air that touch the electrical components that are in the middle. So electrical component that generate and dissipate heat for thermal power. This air touch this component and stays here. So doesn't move from the bottom to the top like in the center, but stays here. It becomes hot, and that's the reason of why the two sides of that panel were so dark. So we discovered the reason. Okay. So what we did is to try to find a solution. But the problem is that at the beginning we have several constraints. The constraints were the fan position. We cannot move the fence. The fence must stay there. The location of electronic components. The electronic components are in the middle. We cannot move the hot components, electronic components in another place. And the dimension of the display. So what we did is just to work on the holes of the airbox, because the client at the beginning put the holes only in the middle, because they say, okay, the components, the electrical components are in the middle, we have to ventilate very well the electrical components, and so let's put bigger holes only in the middle. And this was wrong. So we create also holes in the sides of the back of the monitor, and so we improve the ventilation also in the side of the display. So we solved the problem, and now the display is well ventilated. So the risk of overheating is eliminated, and so now the display is well ventilated and can be used also in those countries where usually we have high temperatures. So like Middle East countries and not only. So they could sell these panels for Cairo airport, Riyadh underground, and train station, and so on. So in this case, they could start reselling this product. Okay, so previously we had a problem of performance, and then we improved the profits, just improving the performance. In this case, the question was sell or not sell. Okay, we solved the problem, now you can start selling. Okay, but anyway, just I show you two examples of thermal management driven by simulation, in particular driven by CFD simulation. But of course, numerical simulation is not only CFD simulation, but also electromagnetic, structural, and so on. This is another case that we performed in the past was the improvement of the performance of the cooling fan of internal combustion engine that we did many years ago. Also in this case, we improved the performance of noise, of power consumption, and also flow rate, so the amount of air that had to cool down the radiator and other components. This is another example of an improvement of, in this case, of this device, always with the CFD and so on. Anyway, I don't want to waste your time. And before, I never explained how much money was the improvement of the thermal management thanks to the simulation. In this case, the customer explained how an optimization and improvement was for the customer itself. So again, of $1.5 million per year. Okay, I have finished. If you have any question, I'm here.
Thank you, Fabio Zanoletti. I'm sure your customers, they loved these numbers and these results of your projects. Is there any question from the audience to Veloxia? No? Okay, that means that you have been very clear. Thank you, Fabio. And yeah, so before we can close this event, I would like to thank all the persons who contributed and made this event possible. Beginning with all the speakers, I asked the speakers afterwards to come here to make a group picture. Please. Then I would like to thank all the event organizers. And this is beginning from my team, Jakob Niederbacher and Peter Leibengut. Then there's Iris Critelli, Lisa Gaia, and Veronica Adami, and Stefan Wieser for as a technical support. And last and not least, I would like to thank you, dear audience, for your interest and your participation. Hoping that Neue Techpark will you soon in future at webinars and physical events. And before you leave, I would like to invite you again to networking afterwards in the Neusteria, where we can sit together and discuss also very practical, maybe challenges you have, and can exchange some business cards and so on. So, and with this, I wish you all the best. See you soon. Bis bald. A presto.